Okay, so this is kind of an interesting problem, isn't it? So let's see here. Now the function in this problem, I'll find my stylus, hold on here. So here's the function in this problem. The function is equal to 1 divided by x minus 1 to the third power, which incidentally is the same as 1 divided by the cube root of x minus 1. Okay, so, all right. Well, is this function defined at x equals 0? In other words, if I had the function evaluated at 0, let me just see here. Hold on. I need a little more space here. Hold on. So this here is my function. Okay, and if I were to evaluate it at f of 0, I have 1 over x minus 1, or sorry. Hold on here. One over 0 minus 1 raised to the third power. And so that's 1 over negative 1 to the third power, which is, by the way, 1 like the 1 over the cube root of negative 1. Is the cube root of negative 1 defined? We know the square root of negative 1 is not defined, but is the cube root defined? It is, and that's right, Jacob, it equals negative 1. So this is going to equal negative 1 over, or 1 over negative 1, that's negative 1. So the function's defined at x equals 0, and it's certainly defined at x equals 28. So what's the problem here? Why is this an improper integral?
When x equal what?
I'm sorry, Lepine?
When x equal 1.
Very good, very good. That's exactly right. This function here, this denominator, cannot equal, x equals 1 is not in the domain of the function, and x equals 1 is between 0 and 28. Very good, Lepine. That's the problem. So that's what makes this an improper integral. Okay, that's what makes it an improper integral. So, well, how are we going to handle this? How are we going to handle this? Let me show you. What we're going to do is we're going to take the integral and we're going to write it as the sum of two integrals. The first integral goes, the limits go from 0 to 1. And the second integral, the limits go from 1 to 28. So the entire integral with limits 0 to 28 is equal to the sum of these two integrals. The first integral going from 0 to 1, the second integral going from 1 to 28. Okay, absolutely true. And now we have two type 2 integrals here because this first integral is improper because the function is undefined at x equals 1. And similarly, this second integral is improper because the function is defined at undefined at x equals 1. And in both integrals, we have the number 1 as a limit. So we got to compute two improper integrals here, two type 2 improper integrals. So I always set my integral equal to I, and I'm going to compute integral I1 and I2. So here's integral I1. Okay, and let me see here, from 0 to 1, we're approaching 1 from the left. So this is a minus here, a little minus. And so the first improper integral equals the limit of this proper integral as t approaches 1 from the left. Are there any questions so far? Okay. Well, u equals x minus 1, du equals dx. So the limits then change, of course, since I'm doing a u substitution here. The top limit here becomes t minus 1 because u equals x minus 1, and the bottom limit becomes a negative 1 because negative 1 is 0 minus 1, right? And the bottom limit was 0. So, you know, you go to an integral with respect to x to an integral with respect to u. All right, and then the antiderivative of u to the negative third is 3/2 times u to the positive 2/3. Hopefully that's, let me know if you having, I think it's clear enough, but I'll make it a little, you know, you can use that zoom on the right to 3/2, 2/3. Notice that I keep the limit there. I mean, I am computing a limit. So, you know, let me keep the limit where it should be until I'm ready to compute the limit. And I'm not ready yet. I have to substitute in t minus 1 and negative 1 into the antiderivative here, into the 3/2 u to the 2/3. Okay, may I go to the next page? Okay, Jacob's good, Tal's good. Jazi's good, wonderful. Maria's good. Okay, let's go to the next page. Let's compute this limit. So here I am, the integral. What I'll do is the 3/2 here, the 3/2, I'll pull that out in front of the limit, right? You learn, how many remember that limit constants you can pull out in front of the limit? Sure, Jacob knows that, and a lot of you do here, Leping and a lot of people, and everybody, right? So I'll pull the 3/2 out front. I'll substitute in the t minus 1 and the negative 1. Now, negative 1 to the 2/3, okay, negative 1 raised to the 2/3, okay, is just equal to negative 1 to the 3rd power squared. That just equals negative 1 squared. That just equals positive 1. So, yeah, you get negative 3/2. Notice I didn't need to draw. I didn't need to. If I were to draw the function, I would see that it would be below the x-axis. But it's okay. We don't need to draw it. We get -3/2. And so our first little integral I sub 1, did it converge or diverge?
Converged.
Converged. Okay. So that means then maybe the second integral, I2, converges also. We have to try to compute it. Now, if this, say this first integral diverged, say this first integral, suppose we got -∞ for the first integral. Would we need to compute that second integral, I sub 2? Or could we just say the entire integral diverges? And I got to be a little careful about this. There's more advanced courses that deal with this. But for our purposes, if this first integral, if we got -∞, would we need to worry about the second integral, computing it, or would we just say
No.
that no? I mean, what are you going to do? You got -∞, right? Even if the second integral converged, okay, you'd have -∞ plus some finite value, say, call it a. That's going to equal -∞, right? So, okay, well, let's go after now the second integral. Second integral was the integral from 1 to 28 of 1 over x minus 1 to the third power dx. And I'm going to replace the 1 with a t here. And I'm going to take the limit of this proper integral as t goes to 1. And we're going from the right. Let's see, does that make sense? Let's see, we go from 1 to 28. And we're approaching the left. Okay. And yeah. So no, we're going from the right. We're approaching 1 from the right. So that's why we have the superscript plus there. And we're going to do the same thing. We're going to do substitution. We're going to convert the integral with respect to x to an integral with respect to u, like we've done here. And I'm going to just kind of let you copy the rest of this. Okay. Let me see one thing here. If I have, yeah. Okay. Okay, so I'll end up getting, well, t minus 1 to the 2/3 power. As t approaches 1 from the right, that's going to approach 1 minus 1 to the 2/3 power. And that's just 0 to the 2/3 power. And so you end up getting 27/2. Okay, and so that integral converged too. So now how am I going to get the answer then for my integral? What am I going to have to do? I got negative, hold on here. I got negative 3 halves for I1, the first integral, and 27 halves for I2, the second integral. How am I going to get my final answer?
Add them together.
Add them together.
And you get 12.
That's right. That's right. So if I may, I'll go to the next page. Are there any questions?
Yeah, I'm still copying.
Okay, Marcus. All right.
Okay, I'm good now. Thank you.
Okay, great, great. Okay, so then here we go. Our integral, when we add up our two baby integrals, we get 12. And that's the area. The integral, that integral converges.
Are we going to go over an example of a diverging integral?
Yeah, we could do one. Actually, I could do one right on the whiteboard.
Okay, I was just curious. If it wasn't part of the plan, no worries, but I was just curious because all 3 of these had been converging.
Well, they're the more interesting ones, Maria. They're the more interesting ones. I'll tell you what, maybe to save a little time, I might be able to, let me see if they have, gotta have one in the ebook, in the textbook. Let me see here, one moment. I wanted to do one more example for your notes. Sometimes examples I do are like different from the textbook examples, so you get a wider variety.
It's okay. If you don't, if you can't, that's okay. I was just thinking if the only difference is that you end up getting infinity, then it totally makes sense. And we don't need to go over an example.
Oh, okay. Yeah, the only difference would be you would get infinity. So like for instance, here I got one. Let me bring up the ebook. Let me bring up the ebook. One moment, class. One moment here. Good question here. One moment here. I just got to find it. Let's see. Thank you for your patience. Yeah, this is one. I'm looking at example 7 in the ebook. Let me go to that one. All right, so I think we're good here. Bring it up here. Okay, so here's an example, example 7 from the ebook, where they want you to evaluate this improper integral. And what's, for example 7, of course, the problem is the x equals 1, the function is undefined at x equals 1, so it's a vertical asymptote. So what they do is they take the integral and they write it as the sum of two integrals separated at that x equals 1 limit. The first integral they compute there. Let me see, one moment, class. Hold on, everybody. Just gotta. Yeah, so you see the work there. You see the work. So there you get negative infinity. And so that means then that first integral was divergent, so that means the entire integral is divergent. You don't need to evaluate it. You just say diverges.
Awesome. Thank you.
Okay, you're welcome. Good, good. We got that in the recording. All right, let me do one more example here to kind of make sure you have a variety. Okay. Okay, let's look at this guy here. Let's look at this problem. Is this improper integral an improper integral of type 1 or type 2?
Type 1.
Good. Good. Because of the infinity there. Okay. So naturally, we have to write this integral as a limit. And if you're ready, we'll move on to the next page to see the solution. Okay, everybody has it copied okay? Okay, thumbs up. Oh, good. Thank you, everyone. Thank you. Okay, thank you. Thank you, everyone. Okay, so, well, that 35, if you don't mind, I'll pull that out in front of the integral. I always set my integral equal to I. That was very helpful for a problem like section 5.6, and here it's probably helpful here too. Okay, it's good to have neat work and so forth. Now this integral, I'm going to do a little, so of course I'm going to write the definite integral, or I'm sorry, the improper integral. I'm going to write it as the limit of the proper integral. The limit as t goes to infinity of the integral from 0 to t of e to the x over e to the 2x plus 3. And at first glance, it looks like, gee, maybe you can't integrate this, you know, but you can actually. You can. You can. You can write e to the 2x power as ex squared, because e to the x times e to the x, the base is the same. So what do you do with the exponents? You will, e to the x times e to the x is e to the x squared, right? So isn't that then just, don't we just add the exponents? And that gets us e to the 2x power. Okay, so that turns out I'm going to use a substitution here. Now this might be, you know, this might be something you wouldn't have thought of, but now in the future you're going to think about doing that, right? You're going to think about that. If u equals e to the x, du equals e to the x dx. And so my integral with respect to u becomes this integral down here. What does this integrand kind of remind you of? You know, we got to get the antiderivative. So what do you think, what does this kind of remind you of?
Something from the table of integrals?
Well, yeah, and what the antiderivative would, do you remember, like in section 5.7 with the partial fractions, you had integrals that kind of look like that? The arctan, that's right. So Nathan, that's right. And Maria was getting very close. She knew it was some formula needed. Okay, we're going to use that formula from section 5.7. That formula, it's in 5.7. Okay, all right. And it's that formula 1 towards the end. Okay, so let's go to the next page if we're good. Are there any questions? Okay. So, all right. This is that formula. This is that formula. And 3 I'll write as square root of 3, quantity square root of 3 squared. And now I have my antiderivative. And I'm going to substitute in e to the t and 1. Let me give you a moment to catch up here. Okay, so now, well, what I'm doing here is, let's see here. I want to make sure. I mean, I know what I have here. So I've drawn a picture of the tangent function below. Okay, so what I want to do is I want to justify how I got here. Well, let's take, so you know the 35 root 3. 35 root 3 is here in front. No problem. Now the pi over 6. Notice that I drew a 30, 60, 90 triangle, right? Okay, there's the 30, 60, 90 triangle. All right, and let me just check one thing here. One moment, class. Just give me one moment. I'm checking one thing. Yeah, actually in Appendix C in the textbook, okay, if you go to like your ebook and look at, I think it's Appendix A, and click on that, it says Appendix, click on the appendix. There's an Appendix C, and Appendix C is the trigonometry appendix, and there's a figure 8 that has like this nice triangle, okay? So, you know, that's there in the appendix. And, you know, this is, again, another reason why I like you to be able to access it. Well, clearly, the tangent of 30 degrees, which is pi over 6, tangent of pi over 6, how's the tangent defined? It is, how many remember this term here, this expression? I learned about it when I was in school. Okay, Maria remembers it. SOHCAHTOA. SOHCAHTOA. So sine is opposite. Tal, remember, Tal's seen it. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So the tangent of pi over 6 is equal to 1 over root 3. And therefore, the arc tangent of 1 over root 3 is going to equal pi over 6. That's how I get the pi over 6. The arc tangent of 1 over root 3 then has to equal pi over 6. So are we good with the pi over 6 part? So far, so good? All right, well, let's focus now on the other part. So you have the arc tangent of e to the t over root 3, but you're going to be taking the limit as t goes to infinity. So e to the t over root 3, what would that equal? What would that equal as t goes to infinity?
One.
Well, hold that thought. Let me write it here.
Yeah.
E to the infinity over root 3 would equal,
0.
well, e to the infinity,
Infinity.
that's infinity. So you got infinity, or this is equal to infinity. In other words, and I appreciate all responses. I appreciate all responses. You're letting t go to infinity here. You're letting t go to infinity, right? So e to the infinity, it gets big, over root 3, it gets big. So essentially what you're doing is you're looking at the arctangent of infinity here. For this right here, as t goes to infinity, it's going to behave like the arctangent of infinity. Well, what would that equal? Okay, what would that equal? Well, based on the graph, what's the
Oh, it goes to infinity at pi over 2.
That's right. That's right. That's right. Very good, Maria. Hold on. I got to get I don't know why my pen's acting kind of crazy here. Hold on. Let me see. Pen's kind of locked up here. Why is it locked up? Hold on. Let me click on this. I'll have to do it with the mouse. Hold on here. Try it again here. Yeah, so based on the graph of the tangent, which everybody should know, I don't know why that's locking up on me. I'll have to do it this way. Everybody knows, or should know, that the tangent of pi over 2, tangent of pi over 2, sorry, I'm going to write this well. Tangent of pi over 2 equals infinity. Because as Marita noted, at pi over 2, the graph goes up to infinity. So this means then that the arctangent of infinity, no, that's right. The arctangent of infinity would equal pi over 2. So this justifies this pi over 2 here. Are there any questions on that? Leping?
Professor, also like 3 over 2 pi is also go to infinity. So how we just decide is
Right. What they want, they want the. You're right. What Leping's saying is that the tangent function cycles, right? It cycles. So how do you know they want the pi over 2? It's just the easiest, and you're right. They should be a little clearer, but it's just we pick like we use the standard graph of the trig function, and that's how we do it. Let me see if there's any other. It's an excellent question, really, an excellent question. One moment on that. Hold on. Hold that thought. Yeah, we just use the standard graph Leping, and that's fine. That's fine. The normally like the arctangent, okay, and arc cosine and arc sine. How many remember, like when you had to compute those values in pre-calculus, you would always work off of the standard, sort of like the standard graph. Maybe in pre-calculus, but by definition, it's this, you're using the standard graph. Okay. Well, then here's the integral. Are there any other questions before I move to the next page? All right, Leping's good. And all right, so what I do is, you know, the pi over 2, if I wanted to just, I mean, WebAssign would accept that answer. Pi over 2 is, of course, 3 pi over 6. I can write the answer in a little bit prettier form, and that's what I do there. And so the integral converges. Okay, are there any questions? How many think, well, are there any questions? How many think this is absolutely fascinating, what you're learning here? How many think this is really, I mean, okay, Jacob's liking it. Just Jacob, you're going to be engineers and scientists and computer scientists, right? And economic majors maybe, chemistry. It would be great for the recording if maybe another person would say they like it. Okay, thank you, Renata. Thank you, Nicole. Thank you, Leping, Sophie, Marcus, Abhidar, Baraka, Samuel. I appreciate it. Okay, I'll stop the recording.